The ideas are quite simple, but we are about to derive the governing equation with some mathematics. Strategy. We have seen that the same strategy in lesson 2, active Mollacking analysis. And we categorize the effects of all elements into two different groups. The frequency domain effects, like cavity, like the gain and the group velocity dispersion, and the temporal effects, like saturable absorber, dynamic gain, cell phase modulation, constant phase, etc. And after that, we can arrive at the differential equation of passive master equation. So what is the strategy for formula derivation? It's the same as lesson 2. We formulate the effects of all elements, then force the output pulse reproduce itself after one trip, except for a constant phase. Okay, so I use this picture to illustrate the idea. Okay. It's big A of the group dispersion relation. A2 A3 to the so you finish one round trip. Okay. Then this pulse has to be the same as the input pulse if steady state is reached, right? So they should be all the same except for two things. One, there is a delay. It takes some time to travel one round trip, right? So in principle, these two pulses should be separated by maybe one round trip time. But that's unimportant for us. So that's one exception. The other thing is the phase curves. They have to be of the same shape, but the constant difference is allowed. Okay, so the symbol is psi. This is so-called carrier envelope phase shift, CEP shift. So even they have different CEP shifts, it's allowed. It does not conflict with the self-consistency requirement. Okay, so if you force them to the same A5 identical to A, the input pulse, then you should be able to get a question. Yeah, you notice at the end of lesson 3, we emphasize actually they happen simultaneously. Why can we separate them? Okay, it's for sure. But in principle, your laser cavity, except for fiber lasers, if you are working with solid-state lasers, you have very thin solid-state crystal inside your cavity. Everything else just mirrors. They do not contribute to GDD or SPM, right? They do not penetrate into the material, just reflect it. So only the penetration through maybe your GaN medium matters. But usually the thickness is very thin. In that case, the interplay between GDD and the SPM is usually unimportant. Then you can separate. But if you are working with fiber lasers, you know pulses travel inside the fiber for long distance. Material plays a very important role. Then the interplay is no longer negligible. And usually it dominates the behavior of the laser. That would be a very different story. Okay. 所以我这一套模型不能处理 fiber lasers。这也是有趣的地方因为 fiber lasers 出来的行为就会跟我们这一个 lesson 所学到的结果有很大的差异，完全不一样，因为它的数学模型就完全不一样。Okay. So this model works for solid-state lasers, but not fiber lasers. Then another important thing is the steady-state pulse is no longer Gaussian pulse, as we have seen in lesson 2. Okay, so here we do not assume any specific pulse shape for the derivation. In lesson 2, initially we take a shortcut. At that time, we assume the steady-state pulse is Gaussian pulse, right? But here, we do not assume it's Gaussian. And actually, at the end of this lesson, you will see the solution is not Gaussian, but second hyperbolic function. Okay. Then we go through the contribution of each element one by one. Cavity effect is better modeled by a transfer function in the frequency domain. There are two effects. Linear loss, okay, because the reflectivity of the mirror could be less than 100%, you have cavity loss, and its linear loss modeled by a transfer function e to the minus LC, where LC is a constant. Okay. Second effect is the time delay. So in the frequency domain, a time delay means a linear spectral phase modulation, e to the minus j omega TR. TR equals L over C, the cavity round trip time. We have known that in lesson 1. But this term can be omitted because the absolute timing is unimportant in steady-state analysis. 反正我只关心 steady-state 到达的时候，这个 pulse 的 shape 长什么样子，所以这个 timing 不重要。这个 term 就可以现在就把它 drop 掉。Okay. So if we assume the cavity loss is very weak, in other words, the loss coefficient LC is much less than 1, then the modified spectrum becomes this one. The spectrum is big A1 to the minus the linear loss times LC is 1, so e to the minus LC is close to 1 minus LC, the first Tyler series approximation. So it's like this, 1 minus LC parentheses times of omega. That's the first step, cavity effect. Any question? Good. Second, the GaN effect. Okay. In lesson 1, we have known the contribution from the GaN medium can be modeled by this formula. The output spectrum, big E prime, equals the input spectrum, big E, times e to the big G of omega, where big G of omega is a complex Lorentzian function. Okay? We have seen that in lesson 1. Now, if we assume this means, remember what is omega tilde? The frequency detuning your carrier frequency. Okay, omega minus omega 0, that's omega tilde. What does this mean? Omega tilde over omega g absolutely much less than 1. What's the physical meaning? So it means frequency detuning compare with omega g, and what is omega g in this model? You still remember? Bandwidth, gain bandwidth, right? For example, if your frequency detuning equals the parameter omega g, you got 1 plus j2, okay? In your denominator. So you can imagine the real part of big G will be reduced, maybe by 50%, something like that. So omega G means your bandwidth, gain bandwidth. So if your detuning is much smaller than the bandwidth, gain bandwidth, that means your spectral width is relatively narrow compared with your gain bandwidth. Okay, so that's the assumption. It also implies this model does not work when your spectrum, pulse spectrum, is so broad, very close to your gain bandwidth limit. Okay, if that happens, then the solution has to be adjusted. There could be no simple analytic solution anymore. Okay? But we expect that happens, right? We expect the passive Morlock lasers eventually give us extremely short pulse where the spectrum is almost the same as your gain bandwidth spectrum, right? But before that happens, we probably can get analytic solution, okay? If this is true, then real part of big G, okay, so we don't care about timing. In the midterm exam, you are asked the meaning or physical mechanism of one term, okay, and some of you might remember that term comes from the imaginary part of big G. It's an extra delay shift due to the lasing gain medium, okay? But as I mentioned, we don't care about the timing. So that term, the imaginary part, can be omitted as well. We only focus on real part. Then the real part has only 2 terms if you use second order Tyler series expansion. The 0th order term and the second order term will be in real part. The first order term is about imaginary part, which can be omitted, okay? But for some reason, our textbook used another symbol, omega c, representing the gain bandwidth. And it's related to the original omega g by a very simple relation shown here. Okay, so I adopt the same notation. So here we see a new bandwidth parameter, omega c. Then if we further assume the gain spectral peak is weak, that is small g is much less than 1, we got this. The new spectrum A2 equals e to the big G, but here we only care about real part. So real part of big G times the input spectrum, big A1. And the real part of big G has been approximated by here, okay? So you have e to the G times e to the minus omega over omega c squared. this is a constant, and the second term is a Gaussian function, right? And A1, by the solution, by the conclusion of the previous slide, A1 is close to 1 minus LC parentheses times big A, okay? So you can combine them together. If small g is much less than 1, then e to the g is close to 1 plus g here. And the Gaussian function is approximated by a parabolic function here, 1 minus LC here. So you have the product of 3 terms, then multiply with the input spectrum, big A. Okay? But we need further simplification. If we only preserve the lowest order terms, 理论上你有2项乘2项再乘2项，你有好多项，对不对？但是有些高阶可以丢掉。For example, LC is very small. G is also very small, much less than 1. So if LC times G, the product of 2 small numbers is even smaller, right? 如果 LC 是 0.1，G 是 0.1，LC 乘 G 就变 0.01 了，更小了。这一项就把它丢掉。Under this logic, you got this approximation. 1 minus LC plus G minus a parabolic function, okay, parentheses times big A. So this is the formula when we consider both cavity and the gain effects together. We got this, okay? But in the future, the small g will be generalized to a function of time, g of t. Here, so far, maybe g is just the constant. If you don't consider the dynamic gain, you only consider a static gain, g is a constant. But in active Molag lasers, maybe we need dynamic gain. Then g can be a function of time. Okay, but that's the next step. Any questions so far? Okay. Third effect is the group delay dispersion effect, GDD effect. Here we assume the GDD-induced spectral phase modulation is weak and predominantly quadratic. Okay, so your phase modulation function is close to this one, minus J D times omega squared. What is D? Okay, it's equal to dg over 2. dg is about beta 2 times L, which is the GDD parameter we defined in lesson 2. Okay, so in principle, big D is essentially GDD, D sub G, differing by a factor of 2 only. Okay, but in lesson 2, we use the symbol big D for another physical quantity, the GVD parameter. We have 2 different GVD parameters. They have different physical units. The first one is eta, the second one is big D. To avoid confusion, I have to explain the same symbol big D here does not mean the second GVD parameter in lesson 3, but the GDD parameter in this lesson. Why there are so many different symbols? Unfortunately, different authors adopt different definitions. And the big D here comes from the textbook. I follow the notation of the textbook. That's why. So how about the modeling? Due to the GDD effect, the output spectrum, big AC, is equal to e to the minus jd omega squared, quadratic spectral phase modulation, times A2, big A2, the output of the previous step. Okay. 好，所以这一项其实就是来自2个假设来自第2个假设。我的 phase modulation 呢，我 基本上只考虑二阶相，高阶我就不考虑。Okay. It also implies when your spectral bandwidth is very broad, this assumption could be violated, right? If your spectrum is so broad, you can hardly assume the corresponding phase modulation due to dispersion happens to be a perfect parabolic function, right? It must have higher order terms, cubic term, first order term, and so forth. Then this model should fail. 所以你已经看到一些痕迹了。我们这个 model 最后得到的 solution may be extremely beautiful, but it does not work when your spectrum is very broad. 所以 maybe 100飞秒这一类的 pulse, okay, but if you have 20 femtosecond or 10 femtosecond pulse, I don't think this model will work. Approximation. We have assumed modulation is weak. So basically, d omega squared is a very small number. Exponential function can be approximated by Taylor series expansion. And the A2, we borrow the result of the previous step. So there are a couple of terms. Okay, so always relate the new spectrum with the original input spectrum, big A. Okay, so you have to multiply the two big terms. There are many, many terms, and we borrow the same strategy, only preserving the lowest order terms. So we got this here. Okay. For example, j d omega squared is very small, much smaller than 1. If it is multiplied with, say, LC, the product is even smaller, then that term is get rid of. Okay. So only the lowest order terms are preserved.